that backbone that was arcing away from you is now an arc in the clockwise direction. Welcome, OChemNinjas. Let's learn how to turn Fischer projections into something a little more useful. The Fischer projection is, there's not a lot of good ways to put this, odd. The Fischer projection is just odd. The Fischer projection has a lot of uses in biochemistry when you're dealing with monosaccharides. It's helpful for distinguishing between the various monosaccharides, but we don't see a lot of compelling use cases for the Fischer projection in organic chemistry. Unlike Newman projections, they don't really help us see the mechanism for any particular reaction. Unlike chair structures, they don't really help us see the most stable orientation for the molecule. In fact, I like to joke with my students, the only thing the Fischer projection is good for is turning back into a line angle structure. Once it's in the line angle structure, finding RNS is much easier, seeing the most stable conformation is much easier, doing elimination or substitution reactions is much easier. It's just much easier to do organic chemistry in the line angle structure. Let's go over a process to turn this Fischer projection back into a useful line angle structure. There are lots of legitimate ways to turn this Fischer projection back into a line angle structure. I'm not concerned with those. I'm going to show you one way to turn a Fischer projection back into a line angle structure. Is it the only way? No. Is it the best way? No. It's my way. And it's the way I'm going to teach you. Can you do this other ways? Sure, I don't really care, but Fischer projections have such limited utility in organic chemistry that it's not really worth taking up brain space with several different ways to turn this into a line angle structure. Let's take a moment to remind ourselves what the Fischer projection represents, and that will make it easier to turn it into a line angle structure. This isn't a video on the Fischer projection or how to make a Fischer projection or how to draw a Fischer projection. I have videos that I'll link to down below if you would like some more information on that. This is a video of turning it back into a line angle structure. Recall that the groups on the horizontal bonds are sticking closer to you as the viewer, and the groups on the vertical bonds are sticking further away from you as the viewer. It might be helpful to use a model kit to abstract what we're talking about. I've built a version of this Fischer projection in a model kit, and you should probably do the same. If you'd like information on the model kit that I'm using, this is my favorite model kit. I've got a link to that in the description down below. So this model kit shows the Fischer projection where the groups on the horizontal bonds are sticking closer to you as a viewer, and the groups on the vertical bonds are sticking further away from you as a viewer. I'm using blue as the top and bottom positions. The red are for the positions on the left, and the yellow are for the positions on the right. What I'm going to recommend then is that we reorient our perspective so we're looking at the Fischer projection from the right when we go to redraw it in the line angle structure. And when we do that, we notice something very interesting. In the traditional perspective, because all the vertical bonds are pointing away from you, that vertical backbone kind of forms an arc that arcs away from you as the viewer. So when you go to reorient your perspective to looking at it from the right, that backbone that was arcing away from you is now an arc in the clockwise direction. And recognizing that clockwise arc of the carbon backbone is an important tool for reconverting this Fischer projection to a line angle structure. So to redraw this Fischer projection, I would number your carbons from the bottom to the top. This is going to be a bottom to top reorientation. The first step I would recommend is redrawing that carbon backbone in the clockwise arced orientation. Start with carbon 1 and draw a bond straight up to carbon number 2. The 2-3 bond arc clockwise, the 3-4 bond arc clockwise, and the 4-5 bond arc clockwise. If there were more bonds, we would just continue arcing clockwise. I would recommend just learning the one method and doing it the same way every time, and that would always be starting with carbon number 1, vertically up to carbon 2, and arcing clockwise until you run out of backbone carbons. From here, it's a matter of adding the rest of the groups. And notice, when we look at it from the right, those yellow groups on the right side of the Fischer projection are now sticking closer to me as the viewer. So when I go to draw in those groups on the new line angle structure, those groups on the right will be closer to me as the viewer, and they will be on wedged bonds. The bromine on carbon number 2 will be on a wedged bond. The OH on carbon number 3 will be on a wedged bond. And the hydrogen on carbon number 4 will be on a wedged bond. The same thing is true with the groups on the left. When I reorient my perspective to look at it from the right, those red groups are now pointed away from me as the viewer, so they will be on dashes. This deuterium on carbon number 2 will be on a dash. The fluorine on carbon number 3 will be on a dash. And the NH2 group on carbon number 4 will be on a dash. This gets all the wedges and dashes in our new line angle structure. Finally, we can add the groups for carbon 1 and carbon 5. Carbon number 1 is a CH3. We can leave it implied. Carbon number 5 is CHO. Do you remember what CHO means? CHO is the condensed formula for an aldehyde. So we would add an aldehyde to carbon number 5. If you need a little bit of help with condensed formulas, I have a video that I'll link to in the description. You can watch for more information on that. And this is the identical line angle structure for this Fischer projection. The backbone arcs in the clockwise direction. Everything on the right is on a wedge. Everything on the left is on a dash. From here, we could do all the chemistry that we wanted. We could assign RNS. We could do any reactions that we wanted. But sometimes it's nice to see it in that regular zigzag line angle structure. I wouldn't recommend going straight from the Fischer to the zigzag line angle structure. You can, I just wouldn't do it. I would go to the arced backbone line angle structure and then to the zigzag backbone line angle structure. The first thing we're going to need is that zigzag backbone. This is going to involve some manipulating the molecule through bond rotations. If you need some help with bond rotations, I have some videos that I'll link to down below about bond rotations that you can watch. We need our 5 carbons for our 5 carbons in our backbone chain. With the zigzag backbone in place, we can translate the wedges and dashes into our new zigzag line angle structure. We need to respect the wedge and dash notation when we move it to the new line angle structure. Some of them may switch as we rotate this molecule around to get it into the zigzag. As we look at carbon number 2, the 1, 2, 3 arc goes in the left to right direction, and carbon number 2 is kind of the point of an arrow that's kind of pointed up. If we look at our zigzag, it's also going left to right, and carbon number 2 is also the point of an arrow that's also pointing up. So our wedge dash notation is going to stay the same here. To get from the arc backbone to the zigzag backbone, all we're doing is a steering wheel rotation to rotate carbon number 2 into place, so the wedge and dash is maintained. For carbon number 3, carbon 2, 3, 4 along the arc is going left to right, and carbon number 3 is kind of the point of an arrow that's kind of pointed up. In the zigzag backbone, 2, 3, 4 also go left to right, but carbon number 3 is kind of the point of an arrow that's pointed down. To get from the arc backbone to the zigzag backbone, we need to flip carbon 3 like a pancake in order to move it into place. Because we're doing a pancake flip to get from the arc to the zigzag, the wedge dash notation is going to flip as well. That OH group that was pointed towards you as a viewer in the arc version is going to be pointed away from you as the viewer in the zigzag version. So the OH group is going to go from a wedge to a dash OH in the zigzag version. Similarly, the fluorine that was pointed away from you in the arc version, when we flip it like a pancake, will now be pointed towards you as the viewer, so the fluorine is going to be on a wedge on carbon number 3. For carbon number 4, it's going left to right, and it's an arrow pointed up. In the line angle structure, it's also going left to right, and it's also an arrow pointed up, so these wedge dash notations is going to be retained. The hydrogen will still be on a wedge, and the NH2 group will still be on a dash. We'll finish with the N carbons. Carbon number 1 can still be implied CH3. Carbon number 5 is still the aldehyde, and we can still draw that in, and now we have the Fischer projection in the zigzag line angle structure version. These are technically no longer identical. These are now conformational isomers of each other since we had to rotate around some bonds, but we can get there by drawing the identical arced backbone version and then flipping it to the zigzag backbone version. And now you have the skills you need to get out of the silly Fischer projection and into the more typical line angle structure.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.